Direct variation gives us the following situation. A number y varies directly with x if there exists a non-zero number k such that y equals k times x. K is called the constant of variation. Let's see how this plays out by looking at the following example. The pressure of a liquid problem. The pressure exerted by a certain liquid at a given point varies directly with the depth of the point beneath the surface of the liquid. If the pressure at 30 feet is 15 pounds per square foot, what is the pressure exerted at 70 feet? Now, this problem can seem like it's a little overwhelming at first until you realize that the equation that we're going to use is just simply the form y equals a number times x. K times x is what we'll begin with. Here we're told that the pressure exerted by a certain liquid varies directly with the depth of the point. So what we have is that pressure varies directly with depth. We can write that down if we allow pressure, the amount of pressure, to equal our y variable, and the depth we'll give by using our x variable. We have the pressure varies directly as the depth. So we write down y equals k times x. Now we're going to try to find the value of k in this formula. And the way to do that is to use the values that we were given in the original problem. We were told that at the depth of 30 feet, so we could put in 30 for x, the pressure was 15 pounds per square inch, per square foot that is. So we have 15 equals k times 30. Now to solve for k requires us just to divide both sides of the equation by 30, and what we get is 15 over 30, which is equal to 0.5. Now what that means is that we can write down y equals 0.5x as the formula which gives us what happens to our pressure according to the depth that we're dealing with. We can look in at our graphing calculator in order to find certain values of what we end up getting in the problem. For instance, it asks us what is the pressure exerted at 70 feet. Let's go back and clear out our screen, and we're going to insert into our equation y1 the equation we came up with, 0.5x. Now I'm going to go to table set, and I'm going to again use the ask feature, and when I go to my table it asks me what is the value that I want to input. I'm going to put in 70, and it tells me that the value is 35, which of course makes sense because we know that if all we're doing is multiplying by 1/2, then what we end up with is 35 here. So at a depth of 70 feet, we have 35 pounds per square foot of pressure. As our next example, we're going to consider an application from business. Let's look at a delivery service and what happens in a case of someone trying to go in business for themselves. Lane Vosberg operates a delivery service in a southern city. His startup cost amounted to $2,300. He estimates that it will cost him, in terms of gasoline, wear and tear on his car, etc., $3 per delivery. He charges $5.50 per delivery. Let x represent the number of deliveries he makes, and find the cost and revenue functions in terms of x. Also, we want to find the value of x for which the revenue equals the cost, or where c of x equals r of x. So let's begin by setting up the function for cost. C of x equals. We're told in the situation that his original cost were $2,300. So we can write that down as part of our cost. But we also have what are called variable costs. These are the fixed costs. Our variable costs are $3 per delivery. So we can write down $3 for each delivery that he makes. Next, we're told that the revenue, the amount of money that he brings in, is equal to $5.50 per delivery. So we can write down r of x equals 5.50x. So we've come up with the two formulas for the cost and the revenue. We next would like to find the value of x for which the cost equals the revenue. To do that, we simply set the two functions equal to each other. 2,300 plus 3x equals 5.50 times x. Subtracting 3x from both sides of the equation gives us 2,300 equals 2.50x, And finally, dividing both sides of the equation by 2.5, we get that x equals 920. Now, what that relates to in the problem is that he needs 920 deliveries in order to break even, where his cost and his revenue are the same value. We call this, obviously, the break-even point. On the graphing calculator, we can also do this same problem. We're going to put the cost function into y1 and the revenue function into y sub 2. And then we'll have to change our window in order to depict what's going on in the problem. So clearing out y sub 1, we end up inputting the cost function, 2300 plus 3x, and our revenue function is 5.5x. You could put 5.50 if you'd like. Now, we have to consider what's going on in the problem in order to set a good window here. What we know is that x stands for the number of deliveries that he makes. So the least number of deliveries could be 0. Let's pick a high number of deliveries in order to give us a starting point. We'll choose 1,500. And I'm going to make my scale 100. Our y value stands for the amount of revenue. Obviously, the smallest amount of revenue you can make is nothing. The largest amount, again, I'm going to choose a fairly large value. $10,000 would be nice to make in a week. We are going to then end up having our y scale equal to 1,000. Graphing these two functions, what we'll be looking for the break-even point would be the intersection of the graphs. We can see that our break-even point is here. To find it in the calculator, we're going to do, again, our intersection method. Our first curve is y1, second curve is y2, and putting our guess approximately on top of that point, we find the intersection verifies what we had found analytically. We end up with an intersection point of 920. By the way, the value of 5,060 that was given there would be what his cost and his revenue were when they were equal. We'd now like you to try one of these problems on your own. So let's look at an example that's similar to the example we just finished with, having to do with cost and revenue. Rebecca Isaac Fahey stuffs envelopes for extra income during her spare time. Her initial cost to obtain the necessary information for the job was $200. Each envelope costs 2 cents, and she gets paid 4 cents per envelope stuffed. Let's let X represent the number of envelopes stuffed. The first thing that you want to do is express the cost C as a function of X. Next, express the revenue R as a function of X. And finally, determine the break-even point. Turn the tape off now and try this problem on your own. Then turn the tape back on in order to check your work. Now let's see if you were able to solve the problem. We're told that we are going to let X equal the number of envelopes that she ends up working with. We want to come up with a function that gives us the cost of her business. We're told that her initial startup costs are $200, so we can write down 200. And we're also told that it cost her 2 cents per envelope, so we can write down 0.02x. Make sure you're using decimals here because you've already used 200 as dollars, so this has to be in the same unit. Next, we want to write down what her revenue is. Her revenue, we're told, is 4 cents per envelope that's stuffed. So we can write down 4 cents per envelope. Did you get the cost and revenue functions right? Well, now let's see if you can get the break-even point. All we have to do is set those two functions equal to each other. We have 200 plus 0.02x equals 0.04x. We now subtract 0.02x from both sides of the equation, giving us 200 equals 0.04 minus 0.02 is 0.02, and then that's the coefficient on x. Next, we divide both sides of the equation by 0.02, and we end up with 10,000, which is a pretty nice number of envelopes that she's going to have to stuff. It turns out that if she stuffs more than 10,000 envelopes, she'll end up making a profit. But if she doesn't stuff that many, she'll end up being in the red. You've now looked at a number of applications for linear functions and equations. It's time to try a few on your own. Use the exercises at the end of the section to try some.